Paolo Morini, vice direttore del Planetario di Ravenna. Qualcuno di voi lo conosce nell'ambito più CPO e per motivi astronomici. Ingegner Morini nella sua attività planetario collabora, e tutti noi che collaboriamo con Planetario, anch'io, collabora con diversi esperti internazionali. Oggi ne abbiamo uno qua con noi che ci racconterà le ultime novità su James Webb Telescope. Quindi l'introduzione del nostro ospite la farà Paolo Morini. La parola a Paolo Morini.
Benissimo, buongiorno ragazzi. Dunque, oggi abbiamo come ospite Derek Demeter, viene dagli Stati Uniti, dirige un planetario in una scuola che è proprietà di una scuola in Florida, vicino a Orlando, dove si chiama Sanford. Derek è qua con noi perché ogni anno negli Stati Uniti c'è un concorso e ogni anno viene selezionato un planetarista americano, un esperto di didattica della scienza col planetario, per un viaggio di 2 settimane in Italia. E quindi noi attraverso l'associazione dei planetari italiani abbiamo chiesto la presenza di Derek, che praticamente farà un pellegrinaggio in tantissimi planetari italiani. Ha cominciato da Perugia, Firenze, Ravenna, poi andrà a Brescia, a Gorizia, farà un tour dei planetari italiani. Ci porterà il suo modo di fare didattica, di fare astronomia, e noi gli parliamo di come la facciamo noi, insomma, e questi sono scambi molto interessanti. Oggi Derek ci ha portato una presentazione sul James Webb Space Telescope. Qualcuno sa che cos'è il James Webb Space Telescope? Avete mai sentito questa parola? No? Allora, il James Webb Space Telescope è un telescopio che lavora nello spazio, è il più grande telescopio spaziale mai lanciato, è in orbita a circa 1,5 milioni di chilometri dalla Terra e, diciamo, già dai suoi primi risultati sta rivoluzionando sia la tecnologia dei telescopi sta rivoluzionando molte conoscenze che abbiamo sull'universo più profondo. Vi dirò solo che i nostri telescopi, se venite al planetario, usiamo i telescopi, noi guardiamo la luce visibile. Il James Webb Space Telescope guarda la luce infrarossa e quindi cosa guarda? Guarda verso oggetti più freddi di quelli che vediamo noi, più freddi delle stelle, e quindi sono oggetti più antichi, per cui si sta avvicinando ai confini dell'universo, diciamo, si sta avvicinando al periodo del Big Bang. Ma ho parlato abbastanza, lascio I give the word to Derek. The lecture will be in English, of course, so we require a special attention by yours. Thank you very much.
Grazie. Buongiorno. Hello. Yes, my name is Derek Demeter, and I come from USA, and we are going to talk about the James Webb Space Telescope. And what I'm going to do here is present it here on the screen and talk a little bit about some of the things that what makes the James Webb Space Telescope special, and then we're going to take a look at many things that have been recently discovered with the James Webb. If you have questions, we will have some time at the end if you're interested in asking. If you have not quite comfortable in English, you can always present that to either one of our teachers or to Paolo here. And I would love to hear what you are interested in terms of astronomy. I'm going to come over here to the computer here, which I will control the objects. So I had a chance to visit the NASA Goddard Space Flight Center. That is where the James Webb Space Telescope was manufactured and assembled. This is a special fisheye lens that allows us to get a really nice view of the facility. This is where the James Webb Space Telescope was designed, and You can see here, that is one of the machines that lift people up. So a human being would be roughly about this size, and that is one of 18 mirrors that James Webb Space Telescope has to view the stars. So it is a very large telescope. It would most likely fit inside, almost inside this auditorium here. So just to give you an idea how big this thing is. When the Space Telescope before it was launched, it had to go through a lot of tests to make sure that it could survive the trip. How many of you have heard of the Hubble Space Telescope? Hubble Space Telescope. This is another space telescope, but it is in Earth's orbit, only about a few hundred kilometers above the surface of the Earth. This thing is over 180 million kilometers away from the Earth. It is truly in space. And in order for it to be launched from Earth to its destination, it had to be put to, oh, okay, thank you. I am normally very loud, so I don't mind being loud, but it does help to have a microphone. You all can hear me, yes? Okay, good. So when the James Webb Space Telescope was put into the rocket, it had to be squished together or folded together. Kind of like when you buy something from IKEA, it comes in boxes and you have to assemble it. That's what they had to do. They had to fold it into a very small package. And then the goal is when it was launched into space, it would slowly unfold over time into its configuration. Everything had to be perfect for this, by the way. If anything did not go right, it completely ruins the telescope. And that is the reason why it took so long for this telescope to be built. It took over 20 years for this telescope to be come from the original drawings to fully assembled and launched. And it cost a lot of money. But here's the thing I want to let everyone know. It took several, $25 billion for the James Webb, but that was over 20 years. And in the United States, we have 300 million people paying taxes. So if you do the math, the average cost of this is less than a cup of coffee for people in the United States. So this is a very, very, very well-funded and very, very cheap way of, or not cheap, affordable way to go into space. But everything had to be perfect. When we launched this telescope into space, everything had to work perfectly because we could not leave and fix the telescope. Now, the Hubble Space Telescope, it could be fixed because it was orbiting the Earth. But because this is very far away in space, we can't go and fix it. So we had to make sure that it was working 100% perfect. Now, this is a collaboration. The James Webb is a collaboration between NASA, which is what we have in the United States, and ESA, which is what you all have here in Europe. This is the European Space Agency, ESA. And when the rocket was launched, James Webb was launched on an Ariane rocket, and this is an Ariane 5, and this right here is a rocket that is launched from a place called French Guiana, which is located in South America. And you want to launch a rocket close to the equator because you have more ability to launch. You can launch the rocket at more speed, so you don't have to use as much rocket fuel. This right here launched on December 24th, 2021. So this was launched from that location in French Guiana, the ESA launch facility. And this rocket took the James Webb Space Telescope into space. So wrong way. All right, so now that the spacecraft was launched, this is the path that James Webb had to take in order to get to its location. So what it basically did is it went from Earth,
it started to slowly open up to its final form. It had to deploy the solar array, which is what they use to power the telescope. It had to get the antennas in place for communication to here on Earth. And it had to make adjustments in its trajectory to get to the exact spot it needed to be. Now, the James Webb is located in a fancy place called Lagrange Point 2. This is an area, the Earth and the Sun have these areas called Lagrange points. There are 3 of them. And the second one is in a way that as the spacecraft is moving, it's moving within the balance between the Sun and the Earth. So as the Earth is orbiting the Sun, James Webb is being held in this one spot, but also moving around the Earth as it orbits the Sun. And at this point, the spacecraft can always remain in the same position. And that's very important. I want to talk about that. That James Webb needs to be in a specific position at all times because it's very, very important to the way the spacecraft works. So we're going to talk about that in a few more minutes. So here we have some of the things that we can find on the James Webb Space Telescope. So one side of the telescope, you can see here, one side of the Space Telescope is the telescope. It's where a telescope, we have the mirror and the secondary mirror. So how many of you are familiar with telescopes? Different types of telescopes. There are 2 main types of telescopes. There are refractors, which use lenses like your eyeglasses. They bend light to a focus, allowing us to see the universe. And then there's a second type of telescope called a reflector telescope. And a reflector telescope, like a mirror, you all use mirrors, right? Of course you do. Or maybe use your phone now, but back in the day we used mirrors. Mirrors reflect light. And this is the primary type of telescope built by observatories in the world now, are reflectors. Why? Reflector telescopes are much, much easier to build than refractors. They cost less money, and you can make them very large. So one side of the telescope, these are all the things that are needed on Earth. So we have the solar shield that blocks the light from the sun. It also powers everything. We have antennas, and just like your phone's antennas, we send radio waves back to Earth to communicate with the spacecraft. So if we tell it what to do, we can plug in a code, we can tell it what to do, and then we can send that code into space to the James Webb, and then the telescope does what it needs to do. We have various types of cameras. So this telescope, instead of looking through say an eyepiece, it has several cameras. These cameras detect light from different wavelengths of light, and it allows us to see into the universe. Just like your phone, when you take a picture with your phone, the CMOS chip, the little chip that's in the camera, detects photons or light and then converts that into pixels. The same thing with the James Webb Space Telescope. Now, remember I told you that the James Webb has to be in a certain configuration. It has to be placed in its right position. And the reason for that is that this telescope does not see the same light you and me see. All right? This is looking at a different type of light we call infrared. How many of you are familiar with the word infrared? Infrared, this is heat light. This is, if you ever seen an infrared camera, and you use an infrared camera, it shows your body heat. If you've seen the movie Predator, that is also the alien from that movie saw in heat. James Webb looks at infrared. What that means is that it needs to be very, very cold. It needs to have the absence of heat. Because if we had heat around the telescope, It's the same thing as if I took a flashlight and shined it in your face while looking through a telescope. It would make it nearly impossible to see what you want to see through the telescope. So, here we have the hot side, which is 85 degrees Celsius, hot. And then we have the cold side, which is minus 233 degrees Celsius. Very cold. So we have to keep the telescope facing away from the sun at all times to allow us to see in infrared. All right, so that's why we have the orientation of the telescope in such a way in order for us to see the universe. Now, you have probably heard of the electromagnetic spectrum. We have different forms of the electromagnetic spectrum. We have the most energetic light in the universe, which are gamma rays. We also have X-rays, ultraviolet, and then one small area of the electromagnetic spectrum is what we call visible light. That's what you, that's what me, that's what everyone sees in the universe. However, that is not what James Webb is trying to look at. James Webb is looking at infrared, which is the heat light that we see beyond visible. Now, why do we want to look at infrared instead of visible light? You might be wondering that. Why do we want to waste our time in a different form of light? Well, think about this. Look at the size of visible light. It is very tiny in terms of the grand view of the universe. Now, but the question is, why do we want to look at infrared? Why not radio? Why not microwave? Well, we can learn about a lot of the universe with infrared. Here I have two images. This image is taken with the Hubble Space Telescope. Now, Hubble, I can show you in the slide again. Hubble, that's Hubble, was looking in the visible light. James Webb is looking in infrared. So this is called a nebula. This is a nebula. This is an area in space where we have gas and we have dust in the universe. So we have gas here, we have dust. And then up here is the same picture of the nebula, except this time, this nebula was taken by the James Webb Space Telescope. Now, when we look at these two images here, what are some of the things that you see that are different? Which one has more detail? The one at the top or the one at the bottom? The top. The top has more detail. Well, that's because the telescope of James Webb is much larger. The larger the telescope, the more it can resolve, the more detail it can see. It's like on your phones, your phone can detect light, but if it has a bigger sensor, when you zoom in, you can see more detail, right? If it's a smaller sensor with less megapixels, is it as clear as something that's bigger? Same thing. Well, the other thing you might notice is there's one other thing that's different between these two pictures besides detail. What do you see more of in the James Webb than you do in the Hubble? Stars. There are a lot more stars in the Webb picture than in the Hubble picture. And the reason for that is because a lot of those stars are not visible with visible light. You can only see those stars in infrared. And many of those stars' light is blocked by the gas and dust. And kind of like a cloud going over the sun, a lot of that infrared is blocked by the gas, or the visible light. The visible light is blocked by the gas. But in infrared, the wavelengths of light can pass through the dust and gas. And so we can see them. So since we can see more stuff with infrared, we can learn more about the universe. So that's the difference of why we see why we want to look at infrared instead of visible light. Now, as I told you before, this telescope has 18 mirrors. Means that it takes 18 separate views of the universe. Now, how do we take 18 separate views of the universe and put them together to make one view? Well, the James Webb has what we call gyrosensors that move the mirrors around like this. And over time, what we can do is we can take the light of those images and correct them to create one full beam of light. So we can collect the light from all of those mirrors to make it into a mega telescope. So you can see here as we move the beams of light, we can then focus the beams of light all onto a secondary mirror that comes together and forms a final form of light that enters the telescope. So by using smaller mirrors, we can make those small adjustments and corrections, and then we can finally get a full image. Now, there are different sensors that the James Webb Space Telescope has. It can look in the near infrared, that means infrared closest to visible. It can look in the mid-infrared, which is in the middle, and it can look in the far infrared. And the detail that the James Webb Space Telescope got is phenomenal. We can see incredible views of the universe. And it took a while to get the telescope that we call calibrated. So we had to adjust the mirrors just right to get the final images. So now that we had from the assembly of the telescope to the launch of the telescope, now to deploying the telescope, to making sure that the mirrors are all put together correctly, now it's time to use the telescope. And so we're going to use the telescope to see what we can see. James Webb is looking at many things in the universe. And what I'd like to do now is talk about some of the things that James Webb observes in our solar system. So we're going to start off with closest to Earth to very far from Earth. Now, can anyone tell me the name of this planet? Jupiter. That's right, this is Jupiter. And Jupiter is the largest planet in our solar system. You can fit over 1,000 Earths inside Jupiter. That's how big this thing is. Well, what are some of the things that we can see better in infrared that we can't see with your eyes? Now, you all can go outside tonight. If the weather is clear and you look to the west and you look over, you'll see a very bright star. But that's not a star. That's the planet Jupiter. And we also have telescopes that we can observe Jupiter from time to time, yes? So at some point, maybe some of you will have a chance to see Jupiter through a telescope. Well, one of the things that we can't see very well in visible light, that we can see very well in infrared, are the rings of Jupiter. Did you know that Jupiter has rings like Saturn? It does. And the rings of Jupiter are primarily made up of rock. And just like when you heat up a stone, it can get very hot. It can absorb heat very well. So because we're looking at heat light, we can see the rings glow very bright under infrared. So we can study the ring system of Jupiter in much better detail than we can if we were looking through a visible telescope. Also, we can see what's going on in the clouds of Jupiter. The clouds of Jupiter absorb a lot of heat, and we can learn more about how the cloud systems of Jupiter, which you can see here in these stripes in the atmosphere, we can learn about how the clouds of Jupiter behave as the planet rotates. Of course, Earth's rotation is 24 hours. Jupiter's rotation is only 10 hours. So one full day of Jupiter is 10 hours long. So because it rotates very quick, it generates a lot of weather systems in its atmosphere. All right, what is the name of this planet? Saturn. So this is Saturn, and Saturn Just like Jupiter, the rings absorb lots of light. They also reflect light because they are made up of ice as well. The average size of a piece of rock in the rings of Saturn is the size of a bus. So next time you see a bus drive around, that is the size of one of the rocks or ice pieces in the rings of Saturn. Also, if you want to know the size of the rings of Saturn, you could place the Earth on one side and the Moon on the other side. That's how big the rings of Saturn are. By the way, Saturn currently, right now, has the most moons out of any planet in the solar system. The current count for moons in the solar system, in Saturn, is 247. 247. Now, one of those moons around Saturn is called Titan. And Titan actually has clouds of methane, but we also found that Titan has liquid oceans on the surface. Liquid oceans. Now, here on Earth, what are the oceans of Earth made up of?
Water.
Yes, water, or agua, right? So, unlike Earth, the liquid on Titan is made up of methane, ethane. It's made up of oils. Yeah, the liquid on Titan is made up of oils. But here's something we recently found out. We found out that those oils are made up of stuff that could make life. We possibly could find life on Titan. Right now, there is a mission proposed by both NASA and ESA called Dragonfly. The idea is to send this little tiny drone to fly around Titan and scoop up liquid and possibly find out whether there's life. Now, the ESA program launched a probe during the Cassini mission called Huygens. And Huygens actually landed a spacecraft, Huygens was a spacecraft that landed on Titan. So we actually have landed something on Titan years ago, and that's how we know what's on the surface. All right, this is a picture of Neptune. And when we look at Neptune with visible light, we see it just as kind of this blue planet. But because of infrared, we find out that we can learn about the cloud systems on the atmosphere of Neptune better than we can in visible light. So by using infrared, we can learn that Neptune has an extreme amount of storms and weather systems. And we also can see the rings of Neptune as well. Now, maybe you're nervous about one day an asteroid hitting the Earth. Anyone concerned about that? Anyone ever worry about whether one day maybe an asteroid could hit the Earth? Maybe a little bit. Well, that's okay because we actually are trying to figure that out. About a couple of years ago, there was the double asteroid redirect test, DART, that actually slammed into an asteroid. This is a video showing that event when that spacecraft hit the asteroid, and it actually was able to move the position of that asteroid enough to change its orbit. That is going to be the best way for us to solve the asteroid problem. If we ever have an asteroid on a path to hit the Earth, all we have to do is push it away, and eventually it will miss the Earth entirely. So we have proved by a mission that we can do that. So we have a way to one day be able to solve the issue of finding something that will not hit the Earth again. So we've looked at the solar system, but did you know that when you look at the stars in the sky, many of those stars have planets around them? We call these planets exoplanets. And right now there are thousands and thousands of planets that we have discovered around other stars. The graph that you see here behind me shows the atmosphere of a planet known as WASP, 3b. And this right here is an exoplanet that contains water vapor in its atmosphere. Now why? Why is that important, you may ask? Well, what is the one thing we need to survive on Earth? Water. If you stop drinking this, could you live for very long? No. Most astrobiologists think that life thrives in environments of water. And most likely, life can form in bodies of water. We think that possibly this planet could have a water cycle, where the oceans evaporate, produce water in the atmosphere, just like we have here on planet Earth. So it's possible that this is a world that either could have life, or a planet that's suitable or can have life live on it. Now, eventually in the future, we will have to leave planet Earth. In about several billion years from now, the sun will get big enough to consume the Earth. And basically the reason for that is because the core of the sun produces energy through fusion. And over time, the sun, as it does that, it begins to expand. And about a couple of billion years from now, if you plan to wait that long, it will eventually consume the Earth. And we have to leave Earth and find a new world. So, just to think that we are constantly looking for new worlds outside of our solar system. This is the nebula, the Carina Nebula that I showed you earlier. This is the same picture, so I wanted to show it again. This is called the Eagle Nebula because if you look at it from far away, this area here looks like an eagle in a nest. This is called the Pillars of Creation. And all these areas, all throughout, you see these little areas here. That is where this nebula, due to gravity, condenses and eventually forms nuclear reactions that are contained by gravity. When this process begins, you have a star. So stars form inside these nebulas right here. Now, as the star forms, it begins to draw by gravity, begins to draw in other additional material. And it develops what's called a propelid, or a protoplanetary disk. And this is when a solar system forms for the first time. Our solar system, the sun, came from a nebula like this one here. The sun formed a protoplanetary disk that eventually led to the development of all the planets in our solar system. And we can see that in great detail here in the James Webb picture. Now, stars, one of the lessons I did in Perugia and Assisi was talking about star formation. Now, our sun, believe it or not, is actually a small star. It's a small star. Now, our sun will fuse hydrogen into helium for a very long time. But eventually, all that hydrogen runs out. And what you're left up with is just helium. But then the star begins to form a new size that will compress the helium into heavier elements. When the star gets to the element of carbon, it will eventually start to fall apart. So what you're seeing here is called a planetary nebula. This is a place where a star roughly around the size of our sun has died or reached the end of its life. And the outer areas of that star have expanded out into space. And this little bright star in the middle called a white dwarf. And this is the remainder of that carbon core found inside that star. Now, this carbon core is very hot. It causes the outer areas to glow. And we've learned about what's inside of a star by seeing this kind of gas surrounding this ancient star. But using James Webb, we've been able to actually see that there's not just one star in this image, there are two. And you can see that the second star is kind of an orangey color. This star system is what we call a binary star system. This means that this star system has two stars instead of one. So, believe it or not, one of its companion stars has ended its life, and then around it is another star, which is really cool. Now, if you have a big star, a much larger star, there is a star in the constellation of Orion called Betelgeuse. Yes, Betelgeuse. And when Betelgeuse finally reaches the end of its life, it will start to fuse heavier and heavier and heavier elements. It's actually doing that right now. The star is a bright red star, which means that it's in its supergiant phase. It has enough mass to continue to compress elements beyond carbon. And when it gets to iron, the energy it takes to compress iron is too strong and too powerful that the star explodes. And it explodes as a supernova. And all of the material that formed within that star is ejected out into space. So all the things known in our universe, all the stuff, the building blocks of everything in our universe are found within supernovas. All the carbon, all the iron in your blood, everything formed from a supernova event. So you all have stuff within you that actually belonged to a star at one point. So you all are star stuff. Literally, you are star stuff. So all the hydrogen, oxygen, carbon, everything within it, star stuff. Now, this is called Cassiopeia A. This is a supernova remnant. So this is the end of a big star. Now, what happens to the core of this star, unlike the core of a star the size of our sun, which ends up as a white dwarf, this star, the core continues to collapse into itself. And eventually the gravity gets so incredibly strong that all the atoms that compress get basically annihilated, and you have what's called a singularity. And a singularity source is where you form a black hole. So black holes originate from these very powerful star explosions. Now, these are galaxies. We live in a galaxy. Anyone know the name of our galaxy? Milky Way. The Milky Way. We live in the Milky Way, and our galaxy is a relatively young galaxy. Now, these that you see here, these are several galaxies that have interacted with each other. This is called Stephan's quintet. And these galaxies have all shaped themselves by collisions. Now, there is a really cool area that just experienced a collision. This is called the Cartwheel Galaxy. And the shape of this galaxy gets its shape from its recent collision. The two galaxies that you see next to it have resulted from this collision. So generally, galaxies come in contact with each other, and their mutual contacts redistribute the stars in those galaxies. The other thing that we see happen when two galaxies collide is we see that all the excess hydrogen in the galaxy comes together to cause new stars. So all that red that you see within the galaxies here, which what James Webb looks at, James Webb found that these galaxies, due to their recent collision, are home to massive star formation. So from these galactic collisions, we see the birth of many stars. And not only do we get the birth of many stars, what could we get as well? Not just stars, but we could get what? Planets, solar systems. So from these galactic collisions result into new solar systems. Yes, so I think it's really amazing to imagine that these galaxies here, because they all move around, because they interact with each other, this leads to the development of new stars and new planets. Now, by using James Webb and combining it with our knowledge of Hubble, we can get a better picture of what our galaxy, or what galaxies look like in shapes and how these shapes change. Notice here with Hubble, the core of the galaxy is very bright. But under James Webb, we can see much more of the core of the galaxy and structure. So we can learn how the galaxies evolve. As they get older, these supermassive black holes within the center of these galaxies distort and twist matter around it and create these very, very intense, wound up areas near the core of the galaxy. When we combine those two together, we can get a better picture of the shape and distribution of stars in the galaxy. Now, this image that you see here, this is the James Webb Deep Field image. Now, any of the objects you see with those spikes, those are stars. Those are stars. So as you can see here, there are many stars within this area here. But anything that doesn't have those spikes, that is another galaxy. There are millions of galaxies, probably even billions of galaxies in this image here. But what's really neat is that sometimes when you get galaxy clusters, meaning galaxies that are instead of just one galaxy, there are many galaxies very close to each other, you get what's called gravitational lensing. Just like a magnifying glass that magnifies light, the light passes through this intense gravitational field and bends around it. What that means is that the light that you see here and here and there and all those ones that kind of look a little stringy or very thin are distorted light that gets magnified around that cluster. In other words, it allows us to see super distant galaxies that have been magnified by gravity. So we wouldn't know about those galaxies unless we had that strong, intense gravitational field. But what's recently happened is that using one of these gravitational fields, we detected this. This is light from a distant star known as Earendel. And Earendel is considered to be the oldest star we have found in the universe, about 13 billion years old. One of the very first stars to emerge in the universe. And because the intense the galaxy cluster together forms very intense gravitational fields, we were able to magnify the light from that super distant star due to those gravitational fields, which I think is absolutely wild to think about, that we can observe these galaxy clusters and we can see things super far distant in the universe. So the last image I leave you here with is a comparison between the resolution of James Webb. James Webb is 3 times bigger than Hubble. Being that it's bigger than Hubble, we can see things that we would normally not see with Hubble, like this right here. When you cannot see it, it's Hubble. When you can see it, it's James Webb. So in terms of astronomy, bigger is better. The bigger the telescope, the more light it can collect. And as you can see here, there's so much that we still have to look at. For example, the data that's being collected by James Webb now will be studied for decades or more, which means that as you all graduate and you might end up deciding to be an astrophysicist or an astronomer, you will be using the data from James Webb for your entire career, because there's so much that we still need to learn about our universe. So I hope that this presentation today has inspired you to continue learning about James Webb and learning about the information we're getting from James Webb and what we can do with that information, and that you can help maybe down the road collaborate on projects that will help us understand the universe. So thank you so much for your time today and listening to me. Thank you very much. I try to get slower just because it can help you understand better. Hopefully you were able to understand a lot of what I said. Yeah, do we have time for a little bit of questions? If anyone has any questions, if you want to go ahead, I guess you feel uncomfortable in English, you can ask one of our teachers here. Otherwise, I'd love to entertain questions. I'm going to go ahead and come up to the front where it's a little bit less on the screen there. Any questions? Okay, yes.
What kind of star is that oldest one?
Great question. So what kind of star is that? It is a very, very young star that has formed. It would have been a supergiant star, but because the light from that giant star has traveled for a really, really far distance, it has redshifted, so the star is more red because of its vast distance. But if you were to rewind time, it would have been a supergiant, massive blue star.
But it will become a black hole.
Most likely, the universe was when it first formed. The only thing available in the universe in the beginning was hydrogen. So usually you had very large stars, and most of the galaxy cores were the result of these ancient stars. So when these ancient stars died, their black holes gave way to what we call active galaxies, which are called quasars, and that eventually evolved into the big galaxies we have today. Any other questions? Space is mind-blowing, right? Yes. I'm sorry, right in the middle. Yeah, so many distractions. Other projects? So one of them is JUICE currently right now. JUICE. Not like orange juice or apple juice, but JUICE is a mission that's going to Europa to study water on the moon of Europa. That's one of the biggest collaborations that's going on right now with ESA and NASA. So maybe in a few years, it'll take 6 years to get there. So Harvard, maybe they have an astrophysics department there, you can join, or you can work here in Europe, and maybe when you graduate from college, you might be working on a mission or data from JUICE. Pretty cool. Okay, well, thank you so much, everyone. Thank you.